So we're going to prove, or we're going to try to figure out if this statement is a tautology, meaning always true, a contradiction, always false, or a contingency based on using logical equivalences. And that's a little bit different than a truth table version. Truth table, basically, the column that represents this proposition would have to be all truths to be a tautology, all falses for a contradiction, and a mixture of truths and falses for a contingency. With logical equivalences, we just basically have to keep using known equivalences to get it down to, is this true no matter what? Is this false no matter what? Or can we just not get there? So the most popular ones to use, the most popular equivalences to use are these three over here. The first one is the one for the conditional, and the other two are basically De Morgan's laws. And breaking down a logical equivalency basically boils down to breaking everything down to ands and ors. That's the only way we really get anywhere. So we're going to take the statement, and just like with an algebraic expression, I'm going to focus on this innermost expression right here. So this expression is equivalent to, now I'm going to replace not P, or P implies Q, with not P or Q. So that's the only thing I'm changing. And the key is to change only one thing at a time. That way you won't get too flummoxed with this whole thing. It can get overwhelming at times. Now, what we notice here is we have an and applied to an or. So we're going to use the distributive property. I did not write that on the right, so I'll just walk you through it here. So this is equivalent to, in parentheses here, so we have negation Q. Now, the way distributive works is the and gets drawn through everything here. So you have negation Q and negation P, and that's one statement, or negation Q and Q. So basically the and gets carried through, and that implies negation P. I feel like I'm missing parentheses there, but I don't think I am. Why don't I make these outer ones brackets? That way it's easier to tell. There we go. Now, I see here that I can simplify this one. I have negation Q and Q. Now, there's a compound statement that can never be true, because a negation and a statement can never be true at the same time. So that means that this gets replaced with an F. So yes, I'm going to copy this all down. Negation Q and negation P, or false. Now, when you or something with a false, you don't need the false, because that's how or works, right? If this statement, if the negation Q and negation P were true, if I or it with a false, I end up with true. If the negation Q and negation P were false, I or it with false, I still get false. So it's one of those absorption laws, basically. So this guy is out. So now we're down to equivalent to negation Q and negation P. Actually, the bracket is now overkill because we've gotten it down to just that now. Implies negation P. So this is much simpler again. Now, I now have a conditional. Okay, it's just that the left-hand side of the conditional is a little more complicated. So I'm going to treat this as the left-hand side of the conditional, and this is the right side of the conditional. Remember that a conditional can be replaced with the negation of the left or the right. Okay, so now let's see where that gets us. Now we're down to at least all ands and ors, so at least this is getting somewhere. Well, the negation of an and, this is De Morgan, right? That is actually, it looks like this last one here. The negation of an and is the or of the negations. So we have the negation of Q, or the negation of P, or the negation of P. Now, by the double negation laws, we know the negation of the negation is the original. So we have Q, or P, or negation P. And now we have a string of ors, which means we can use the associative laws to take any two out of the three that we feel simplifies the best. And boy, would you look at this right here. P or negation P is true. If you have one or the other, if they're opposites, that means you've encompassed the entire thing. So that means that this is Q or true. And if you or anything with a true, you end up with a true. And that means that this original statement was a tautology because we were able to use valid logical equivalences to get from one step to the next until eventually getting to something that's true. So what that means is, regardless of what the truth values of P and Q are, that statement is always going to be true, regardless. So let P and Q be any statement you want them to be. There it is. Okay, so that's proving a tautology by using logical equivalences. And again, had it ended up being an F, that means it would be a contradiction, which means it's never a true statement. Thanks for watching. Hopefully that helps. Just remember, step by step gets you there. Okay, thanks for watching.